Hey good people, welcome back. In this video, we're going to look at the difference between one-sided and two-sided hypothesis test. I decided to make this video because a few of you had questions in our video meeting last week. So hopefully this will help you develop those hypothesis tests and decide which type you're using, a one-sided or two-sided alternative. We're going to look at 4 questions from the textbook in this video. These first 2 questions we're going to look at only ask us to write the null and our alternative hypothesis for a few different situations. And then we're going to go through a really in-depth example. And I already typed out the solution to that, so I'll do a good job describing it. And this one I'm going to answer in real time just so you can hear my thought process. I didn't even do that problem yet. So let's go ahead and look at the first question. You can pause the video, try to come up with them on your own. All right, write the null and alternative hypotheses you would use to test each of the following situations. A governor is concerned about his negatives, the percentage of state residents who express disapproval of his job performance. His political committee pays for a series of TV ads, hoping that they can keep the negatives below 30%. They will use follow-up polling to assess the ads' effectiveness. So I guess in this one, I would say that the P, or proportion, is the proportion of people who express disapproval for his job performance. So before we did these TV ads, the proportion or the percent of people that expressed disapproval, his negative percentage, was 30%. So we're going to keep our null hypothesis that it did not change and it remained at 30%. Should use an equal sign here. And the alternative hypothesis is that the TV ads actually improved his situation and less people think negatively about his job performance. So our alternative is that the percent of negatives have actually decreased. All right, another situation. Is a coin fair? So I guess if you were checking to see if a coin was fair, you'd have to check to see if the proportion of time it lands on heads is equal to the proportion of time it lands on tails. Let's just choose one of them. Let's just say we'll let P be the percent of time it lands on heads. So our null hypothesis is that the percent of time it lands on heads is the normal thing that you would expect, 50%. And our alternative hypothesis, since we don't know if this thing favors heads or tails, but we're testing to see if it favors one or the other, we're just going to check to see if it doesn't land on heads 50% of the time. So our alternative in that one is a two-sided alternative hypothesis, because we'd be equally interested in it deviating from that mean on the higher side or the lower side. All right, another situation. Only about 20% of people who try to quit smoking succeed. Sellers of a motivational tape claim that listening to the recorded messages can help people quit. So I guess if we set P as the proportion of people who try to quit smoking that actually succeed, our null hypothesis is that it remains unchanged, and the proportion of people that actually succeed is only 20% of them. Now, with the use of this motivational tape, the sellers of the tape hope to improve the rate of people that can quit. So they're hoping that this is going to be higher than 20% of people can quit. So their alternative hypothesis is that the proportion of people that can quit is greater than 20%. All right. And I am going to upload the book solutions to these problems as well, so you can see how the authors of our textbook wrote out these solutions. Another one, very similar question. We're just developing the null and alternative hypotheses for each situation. In the 1950s, only about 40% of high school graduates went on to college. Has the percentage changed? Okay, so our null hypothesis is that the percentage hasn't changed and it remains 40%. And the alternative hypothesis that we're exploring is the possibility that it has changed and it's no longer 40%. they don't suggest that it's increased or decreased, so we're just going to say a two-sided alternative hypothesis. We're just exploring the possibility that it is changed from 40%, and we're looking in either direction. All right. 20% of cars of a certain model have needed costly transmission work after being driven 50,000 and after being driven between 50,000 and 100,000 miles. The manufacturer hopes that a redesign of a transmission component has solved this problem. So 20% of the cars need to have their transmission fixed. That's our null hypothesis, that it has not fixed the problem, that it stays the same. Our null hypothesis is that it's still 20% of them need to have the transmission fixed. And the manufacturer hopes that this redesign has actually improved the situation and less of the cars will require this costly transmission work. So the alternative hypothesis is that fewer proportion of the cars will need this transmission to be fixed. So we're going to set a alternative as P is less than 20%. All right. One more. We field test a new flavor soft drink, planning to market it only if we are sure that over 60% of the people like the flavor. So before, our null hypothesis is that only 60% of people like the flavor, and we're going to market this soft drink if we can find that more than 60% of people like the flavor. So that's what we're going to test as our alternative hypothesis. All right, so those were quick little setting up alternative and null hypotheses, and let's do a real problem now. You can pause the video if you'd like, take a moment to read the problem. So this is about a credit card offer that a company's thinking about sending out to their customers. Sometimes credit card companies will send out a promotional offer hoping to have you change your credit card rate. Some people might take a different credit card rate if they're going to be given points, or they might sign up for a credit card if they're given some type of incentive. In Chapter 18, Exercise 16, you learned that First USA, a major credit card company, is planning a new offer for its current card holders. First USA will give double airline miles on purchases for the next 6 months if the card holder goes online and registers for this offer. To test the effectiveness of this campaign, the company recently sent out offers to a random sample of 50,000 cardholders. Of those, 1,184 registered. A staff member suspects that the success rate for the full campaign sent to 2 million cardholders will be comparable to the standard 2% rate that it is used to seeing in similar campaigns. What do you predict? All right, so we have to do 3 parts. What are the hypotheses? Are the assumptions and conditions for statistical inference met? Do you think the rate would change if it uses this fundraising campaign? Explain. We're going to use a hypothesis test to make that decision. So first step, what are the hypotheses? Well, the hypotheses are, is it going to see the typical 2% success rate that it's used to seeing? Or are we going to see something different? Since it doesn't suggest in the problem that the success rate will be better or worse, I'm going to set my alternative as a two-sided alternative, simply because all it says is that a staff member, suspects that the success rate will be the standard 2% that they're used to seeing. So our alternative is that it's not going to be 2%. And there's always little context clues to help you decide what type of hypothesis test you're doing, what type of alternative, if it's two-sided or one-sided. There's something in the book that suggests that some scientific research companies only use two-sided tests, and that's so that it's harder to prove statistical significance. But you can read about that in Chapter 18 or Chapter 19. So let's keep going. We have our null and alternative hypotheses. Are the assumptions and conditions for inference met? Well, we have to look at these conditions. The independence assumption, the randomization condition, the 10% condition, and the success failure condition. Can we assume that each person's likelihood of accepting the offer is independent of the other person? Yes. Their decision should not depend on whether or not somebody's accepted the offer. The randomization condition, is that met? In fact, it does say that they sent this offer out to a random sample of 50,000 cardholders. So yeah, that's met. The 10% condition. Did we oversample our population? Well, their entire customer base seems to be 2 million cardholders. Is 50% is 50,000 more than 10% of that? Let's see. If it is, that's a problem. Is this greater than 10%? Because you're not supposed to oversample. If you start to oversample, you start to change how many things are left in your population, and they start to actually become dependent. All right, so that's only 2.5%. That's significantly less, so we're good there. We didn't go over 10%. The success failure condition. In our random sample, would we expect to see at least 10 successes? So our typical success rate is 2%. So we have n times p. Is that at least 10? Oh, it's 1,000, definitely. What about n times q? The complement of 2% is 98%. So would we expect to see at least 10 failures? Yeah, we would expect to see 49,000 people reject the offer. So we satisfied the NP-NQ condition. We'd expect to see at least 10 successes and at least 10 failures. You can read more about those conditions for inference if you'd like. Here it is. I'm going to just go on to the next screen. You can pause it here if you'd like. And our last question is, do you think the rate would change if it uses this fundraising campaign? Well, we're going to actually conduct a hypothesis test now. We're going to perform the mechanics of that test. So our first step is constructing a normal model with the mean and standard deviation based off the proportion specified in the null hypothesis. So what was our proportion specified in the null hypothesis? 2%. And our standard deviation, we use that same 2%, and Q is the complement of that. And we use the 50,000 from our sample size. And we get our mean and our standard deviation. Now we're going to build that normal model based off of this mean, and we're going to count that standard deviation 3 times in each direction. To do that, I like to use this little trick on my calculator. I go 0.02 plus 0.000626 x, and what that does is it counts that many multiples of that standard deviation in each direction. And I just go on either side of the mean 3 times. So I use these numbers here on this table, and I just kind of fill them in my normal model, and I rounded it on the normal model there. And next, we plot p hat on the normal model, our sample proportion. Since we're conducting a two-sided hypothesis test, we also plot another p hat on the other side of the mean, the same number of standard deviations away from the mean. So I'm going to plot my p hat. My p hat was 1,184 people accepted the offer out of 50,000 that they sent it out to, which is 2.368% or 0.02368. And that would actually be all the way over here. I think I run out of room. And since we're going to... Actually, let me draw that out for you. There you go. It's actually about close to 6 standard deviations away from the mean, just shy of 6. And since we're doing a two-sided hypothesis test, we're going to plot that number on the other side of the mean as well. So I just plotted it over here. Now, what we really want is the p-value, okay? The p-value is the probability of the sample proportion deviating this much or more on either side of the mean. So given that this is really going to have a 2% success rate with a standard deviation of 0.000626, what's the likelihood of obtaining a sample proportion this far from the mean? or even perhaps further on either side of the mean since it's a two-sided test? Well, let's figure that out. I like to just find this area and then multiply it by 2 because this is completely symmetric. Okay, so to do that, we're going to use the normal CDF on our calculator, the normal cumulative distribution function. So I'd like to just go into second vars, second option there. I'm going to set my lower bound at that cutoff value 0.02368. The upper bound all the way at infinity. Our mean was 0.02. Our standard deviation 0.000626. And we get, wow, that is a really small number. And we have to multiply it by 2 because there's 2 of them, one on the right side and one on the left side. So our p-value is almost 0. So I used a normal CDF. I did this, multiplied it by 2. Our p-value is 0.0000000042, which is, for all intents and purposes, it's basically 0. By the way, here's another way you could do this. If you're watching this video, here's a little statistics gold membership. Another way you can get this answer really easily without doing all this. You go into stat. Don't tell anyone about this. This is a secret. You go into stat. You go to test. You go to 1 proportion z-test. And you just specify that p sub 0 is your null hypothesis value, so it was 2%. The x value is the number of successes that you got in your sample. So we had 1,184 people accepted the credit card offer, and n is that sample size. And you have to tell it if you're doing, oh, that should be 50,000. You have to tell it if you're doing a two-sided alternative, a left-tailed alternative, or a right-tailed alternative. This one we were doing a two-sided alternative. And just hit calculate, and we should get the same answer. See that number at the right here, 4.17 e negative 9? That's the same as this number here. They're off a little bit because I did estimate that standard deviation here, and in the calculator they never ended up rounding that. So I guess the calculator one is a little bit more precise, but they both round to 0.0000000042. So that's another way you can get your answer. All right, what does this answer mean? Let's think about it. Do you think that the rate would change if it uses this fundraising campaign? Well, our p-value is tiny. It's almost 0. Since the p-value is less than 5%, we can reject the null hypothesis. The extremely low p-value is strong evidence that the success rate after offering double airline miles will not be equal to the typical 2%. And the sample proportion helps us decide which way it would actually go. Would it be less than 2% or higher than 2%? The sample proportion of 2.368% suggests that more than 2% of the customers will register for the credit card offer. All right, so again, you can look at the book's solution to the same problem. I'm going to upload that as a PDF file along with this post. All right, let's look at a new problem. I didn't even read this one yet. I'm going to do it in real time to show you how I think about this. Lost luggage. An airline's public relations department says that the airline rarely loses passengers' luggage. It further claims that on those occasions when luggage is lost, 90% is recovered and delivered to its owner within 24 hours. A consumer group randomly surveys a large number of air travelers and finds that only 103 of 122 people who lost luggage on that airline were reunited with the missing items by the next day. Does this cast doubt on the airline's claim? Explain. Let me just first investigate this p-hat. What does this actually equal? And that'll help me decide what type of alternative hypothesis I'm using, because it's not even really, it's not telling us what to do here. We're actually given a lot of freedom in this problem. All right, so this is equal to 0.844, which is less than the airline's claim. They claim that 90% of their customers are reunited with their lost luggage within 24 hours. And in this random sample, only 84.4% of them were reunited by the next day or within 24 hours. So I'm starting to suspect that they're being a little overzealous with this claim, and that the true proportion of people that are reunited with their luggage is actually less than 90%. So I'm going to say that my null hypothesis is that the airline's claim is correct, that 90% of people are reunited with their luggage in less than 24 hours. And my alternative hypothesis is that it's actually less than that. Less than 90% of them are reunited with their luggage in less than 24 hours. All right. The next thing we really have to do is build a normal model based off that null hypothesis. So I'm just going to draw a rough sketch. Center it at 90%. I'm going to count 3 standard deviations in each direction. And I'm going to use my formula for my standard deviation. 90% is our P. Our Q is therefore 10%. And our sample size is 122 people. So our standard deviation is 0.027. So I'm going to count that many standard deviations on either side of the mean. 0.027 standard deviations on either side of the mean. So we get 0.819, 0.846, 0.873, 0.927, 0.954, 0.981. All right. So this had a mean of 0.9 and our standard deviation was 0.027. All right, so the next thing I'd like to do is plot p hat on this normal model. P hat is 0.844, and that puts us right about here. And I'm going to shade in the area in the direction of our alternative hypothesis. So we were interested in the possibility that fewer than 90% of people were reunited with their luggage within 24 hours. So I'm going to say this side. So we need to find that area. So I'm going to do second vars normal cumulative distribution function. And I'm going to go from negative infinity all the way up to this cutoff value 0.844. My mean for this model was 90% and my standard deviation was 0.027. What is our p-value? Let's see, it's 0.019, so that's still a pretty small p-value. Is 0.019 less than 5%? Yes, it is less than 5%. So that's enough evidence for us to reject our null hypothesis. So I'm going to say, since the p-value of 0.019 is less than 5%, there is evidence to reject the null hypothesis. I'm just going to say we should reject the null hypothesis. Therefore, there is evidence that fewer than 90% of people are reunited with their luggage within 24 hours. All right. Just to show you again how to use that trick on the calculator to get that p-value right away, you just go into stat, go over to test, use the one proportion z-test, that's the fifth option there, set your p sub 0 as your null hypothesis, in this case it was 90%, set your x value as the number of people who were reunited, in this case with their luggage, in their sample of 122 people. And then you have to say which side your alternative is going. Our alternative is a left-sided alternative since it says p is less than 90%. Then go to calculate, and you'll see the same p-value here. 0.019 is what I got when I did it, but I did some rounding. This 0.020 is really close. It's within a thousandth of my p-value. All right, so this is the end of the video. Thank you for watching. There's a new assignment that was uploaded on Thursday. It's not due until Friday the 22nd, so you'll have some time to get that done. And you can ask me some questions in our next two video meetings if you need help, and I look forward to seeing you there. Thank you for watching.